wave interference and sound beats. The principle of superposition tells us that when two or more waves meet, the resultant waveform is the sum of the individual wave displacements. So we can write the waves in the following mathematical forms, where A is the amplitude and F1 and F2 are the separate frequencies. So here they have identical amplitude but different frequency. Using the principle of superposition, we sum up the waves, and we also apply this trigonometric identity to get to this final formula. What's important about this final formula, it has two terms. Okay, this term here corresponds to the tones that we actually can observe. Okay, and this F bar is an average of the two frequencies, the two tones combining. So what you physically hear is a combination of these two tones. However, the overall wave is modulated by this term, and this is the beat frequency is kicking in here. This is what dictates the beat frequency, where FB is the beat frequency, and it's the difference between the two wave frequencies. This is important for the coding and how students can write the code for the beat. Here we have a visual representation of two waves meeting. They combine and they produce a new waveform, which is modulated by the beat term here, and this what is produces the beat. So this is like quiet, loud, quiet, and we can click here to listen to examples of beats. So if we play two frequencies of the same tone, we don't hear any beats. They match up. One is because the difference between the two frequencies is 0, 500 minus 500, and the average is also 500. Now let's make one of them 501. We can hear the modulation, this loud, quiet, loud, quiet. That's what the beats actually are. And the beat frequency is 1 Hertz because it's the difference. The tone that we're listening to is the average of the two, which is 500.5 Hertz. Let's step up this frequency, and we can hear a higher beat frequency because it's 2 Hertz. And we can keep going. I can jump up, make it even higher. Here we have some sample code for the Arduino board. And what I want to bring your attention to is these two libraries. Liquid Crystal is for the shield to display the frequency values, and Tone H is a library that allows us to write different tones to different speakers on the same Arduino board. I introduced some variables here. The minimum frequency is where you want to start with one of your speakers, and the maximum frequency is where you want it to finish, and the reference frequency is the frequency in the middle where you want the frequencies to pass through. The int frequency is basically the interval range, so we're going to go in steps of 2 Hertz from 450 to 470. Again, these can be changed, and I can show you in a minute what that would sound like if you changed. What I like about this, it gives students the opportunity to play around, to play with the code, to adjust values, but not only to do that in a software term, they can see the physical, influence, of changing software code. They can hear it, they can see it with the LED. And I feel this is a very important educational process. So earlier on we saw the mathematical approach. Here we can see a coding, more STEM engineering approach. So what I'm aiming to do is to bring physics and the maker approach closer together within the classroom, within the school labs. I think it's a very important process and something very exciting to do. I'm going to demonstrate the beatbox with the Arduino board, an LCD shield, and 2 piezo speakers. So I'm going to connect the Arduino board to the computer just for some power, and I'm going to demonstrate the beat effect. I want you to notice a couple of features here. One is the sound, the actual beats that you hear. So that's this modulation or on and off of the sound at a certain frequency. I want you to look at the LCD display, which tells you the frequency of the 2 speakers. And if you like, you can calculate the beat frequency by subtracting the 2 separate frequencies. And I also want you to look at the flashing LED, which also flashes at the same frequency as that of the beats. So there are kind of many aspects here going on. One is sound, one is the display, and the other is also the LED. So many different aspects I want you to look out for. Okay, so let's go. So here we can hear the high frequency beats. And now the frequency starts to decrease again, the second speaker. So our beat frequency will get lower. So now I'd like to repeat the same experiment or demonstration, but changing the minimum frequency. So I'm going to change it from, instead of 450 hertz, that's for one of the speakers, I'm going to go 1000. I'm going to set the maximum frequency to 1020. And the reference frequency, which is the fixed frequency of one of the speakers, is in the middle. So I'm going to say 1010 hertz. I'm going to save that and re-upload. And let's listen and watch the beat effect. Some concluding remarks about the beatbox. It was a very enjoyable project. I learned a lot. Sometimes it's easier to stay with traditional physics teaching. However, we've got to try new approaches for students, most of all, for them to learn in different types of ways. So that's really what I like about the maker philosophy, is that you're free. You can find your solution, for your classroom, for your students, for their learning. And I like the idea of blending more and more physics and the maker approach, because there's so many possibilities, so many alternatives, and so much creativity that you can bring into physics teaching.